Welcome back to Differential Calculus. In this video, I want to go through properties of limits. I always hate the term, but a lot of sources call these properties the limit laws. It's a foundational thing that really doesn't matter in this course, but it's one of my soapboxes, so forgive me as I climb on it for a moment. The idea of a law in mathematics is generally taken to mean something that we are basing our theory on. And the limit laws do not satisfy that definition whatsoever. If you go further in mathematics to take a third or fourth year course called real analysis, one of the most important things you're going to do in that course is show that that ugly epsilon delta definition of a limit is enough to verify that the limit laws must work the way we say they are going to. And so that's why I like calling them the properties of limits instead. Properties are things that we derive from a more solid foundation. And that's what's happening here. So that's why I use that vocabulary, which is not rare, but not the most common either. All right. Off of my soapbox, we'll start off with the easiest ones. The limit as x approaches c of some constant a is equal to that constant. And the limit as x approaches c of x is equal to c. I think that these two limit laws, these two properties, are fairly self-evident. If you are following along on the line y equals a, no matter where you are, the line is just going to keep being at a. Nothing happens there. If you're following along on the line y equals x, whatever x you are looking at, the y is the exact same thing. So if you follow along that line until x equals c, you're also going to be at the point y equals c. If you're not sure, try graphing those functions, y equals a and y equals x. Pick some point c, see what you get out of it. Follow the path to see what happens. All right, those are the obvious ones. The other properties here are not quite so obvious. The most important is the idea of linearity. We're going to see linearity an awful lot in this course. All of the important functions in calculus follow the idea of linearity. Linearity says that for real valued functions f of x and g of x, and for constants a and b, the limit as x approaches c of a times f of x plus b times g of x is equal to a times the limit as x approaches c of f of x plus b times the limit as x approaches c of g of x. Right. 3 properties in, and we really can get somewhere already. For example, if I want to take the limit as x approaches 4 of 3x minus 5, according to linearity, This has to be the same thing as 3 times the limit as x approaches 4 of x minus the limit as x approaches 4 of 5. The constant rule tells us that as x approaches anything evaluated on a constant function, we get back that constant function. The x rule, or the identity rule, tells us that if we take the limit as x approaches anything of x, we get the thing we are approaching, 4 in this case. So we have 3 times 4, which is 12, and then 12 minus 5, which is 7. Yes, this is exactly what you would get if you take 3x minus 5 and evaluate when x is equal to 4. Yes, I am well aware that I am taking a very long way to get there. The point here is not learning how to evaluate things. The point here is looking at well-behaved functions and learning the vocabulary, learning the terminology, and learning the processes that we are and are not allowed to follow. Because we are going to get to weird things. When you are dealing with piecewise defined functions, this goes from being dead simple to making you want to tear your hair out. But if you know what you're doing, you know how to keep yourself organized, everything will work fine. When we get to some functions that are not defined at points, this is going to make us want to tear our hair out. But if we know what we're doing, we'll be fine. The other really fun one, we're going to start looking next week at, instead of approaching a point, what if we want to go to infinity? It's going to feel very different. Evaluating a function at infinity is nonsense. But with the power of limits, we'll be able to do it, following the same process. So today we are looking at continuous functions. Continuous functions have incredibly well-behaved limits. We are taking a very long way to get to a very simple result. We're learning the process on the easy ones, so when we get to the hard ones, we know what we're doing. The next rule is the power rule. Again, we're going to look at any real valued function f and take the limit as x approaches c of f of x raised to some power, I'll call it n. And we're going to get the same thing if we took the limit as x approaches c of f of x and then raise that whole thing to a power. And thanks to how wonderful the power rule works, we can now deal with any sort of polynomial. The limit as x approaches 2 of 5x cubed minus 3x squared plus x. I'm not going to write it out in multiple steps. Using linearity, we can split this thing up. Using the power rule, we can get inside the exponents, and we can write this as 5 times the limit as x approaches 2 of x cubed minus 3 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of x. And then using the identity rule, the first one we looked at today, the limit as x approaches 2 of x is in fact 2. Right. 2 cubed is 8, 5 times 8 is 40, 2 squared is 4, 3 times 4 is 12. 40 minus 12 plus 2 is 30. The product rule, again, I'm assuming that f of x and g of x are two real valued functions. The product rule tells me that the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. The quotient rule. The quotient rule is where things start to get interesting. Quotient rule tells us that the limit as x approaches c of the quotient f of x over g of x is in fact equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. But this one, finally, we get to a place where we have a caveat. This rule only works, let's try writing the word whenever so it looks like a word. Whenever the limit as x approaches c of g of x is non-zero. Of course, if the limit as x approaches c of g of x was equal to 0, then we would be dividing by 0 in the denominator here. Dividing by 0 is a bad thing, so we have to make sure that that doesn't happen. An interesting thing, something we'll get to a little bit later on in the course, if that limit happened to be 0 in the denominator, that doesn't necessarily mean that we're done and we're out and the limit doesn't exist. There are tools, and we looked at some in a previous video, there are places where that limit can still exist. And so we will develop some more tools for dealing with quotients when you happen to be dividing by 0. But for right now, let's just look at the simplest cases. So yes, whenever you are looking at a product or a quotient, things still behave nicely. So for example, if I want to take the limit as x approaches 0 of x squared plus 2x plus 5 over x squared minus 9x plus 10, I'm not even going to bother writing it out. We can plug in, we can separate out, take the limit of the numerator and the limit of the denominator. We can dig into taking the limit of each piece of the polynomial in the numerator and each piece of the polynomial in the denominator. And we can get things that work fairly nicely. We get 0 plus 0 plus 5. We get 0 minus 0 plus 10, which simplifies down and becomes 1/2. Again, it is important to note here that this behaved very nicely. We happen to be evaluating the limit of a rational function at a point where the function is continuous. And when functions are continuous, their limits are well behaved, which is a very backwards way of saying things. The whole goal of limits, which we'll get to in a future video, is using limits to show when a function is continuous. But I'm not going to pretend you haven't taken previous math courses. You've learned that polynomials are always continuous, that rational functions are continuous except at the points where the denominator is 0. Those are going to be true. And when we have those situations, it means that the limit works very nicely indeed. The last thing I have are roots and radicals. And in this instance, we really do have to be careful about our caveats. We're going to say that the limit as x approaches c of the nth root of f of x is equal to the nth root of the limit as x approaches c of f of x. And radicals can be weird. Whenever the index of the radical is odd, if n is odd, this is true for all f of x and for all c. If n is even roots are only defined for positive values inside. So if n is even, this is true only if there is some open interval zero less than the absolute value of x minus c less than delta. That looks familiar. That's right from the definition, the epsilon delta definition of the interval, or of the limit. I said that's an open interval. It kind of mostly is. It is the interval from c minus delta to c union with c to c plus delta. Right, so it's not quite an entire open interval. It has excluded the point c itself from the interval because, as we've seen dealing with limits in the past, we don't care what happens at c. But we have to have some open interval where f of x is greater than or equal to 0 for all x in this interval. If you have a situation where you cannot figure out a way to write this interval because f of x is not defined in the interval, well, then the inner limit isn't going to work. Right? I'm not even thinking about whether or not f of x is defined in this interval. If it's impossible to find this interval where f of x is always defined, then the limit as x approaches c of f of x isn't going to work in the first place, and none of this will be of any value. So assuming that we have that, we are going to insist that the value of the function is always positive. Right? The interval does not have to be big. The interval can be incredibly tiny, but it has to exist. There has to be some fuzziness to the left and right of the c where this happens. If you happen to have picked a function f of x where the function is equal to 0 and it's negative to the left, positive to the right, you're never going to be able to find this interval. Right. So if f of x looks something like that, then this whole process is going to fail. But if you've got your point c here, and your function is doing something that kind of looks like that, all right, well, I have to go into this very small window inside there, but it does exist. And I can just stay in that interval and everything will work out fine. And so I'll leave you with this limit to think about. Using the properties of limits, the limit laws that we talked about in this video, I would like you to evaluate the limit as x approaches 5 of the function 2x plus 1 times the square root of x plus 11. Take a few minutes, see what you get with that, and I'll see you in the next video.